Today let's look at something that's really at the fundamental of deep learning and machine learning. And if anyone that is familiar with these concepts understands that this is not something someone can talk about very lightly, and involves a lot of math and a lot of intuition to fully grasp. But this is meant to serve as more of a gentle introduction to the concepts and just a high level overview of what these concepts mean, so that you can uh, feed your curiosity essentially. So, what is a neural network and what is backpropagation and gradient descent? So, let's start with what a neural network is. A neural network is essentially supposed to mimic the way our brains work, and this is essentially replicating how our brains accept information and is able to infer on them. So let's first look at the diagram of a basic neural network, and then we'll dive a bit deeper into it. So we have this, and then something like this. So what is this? So this is something called the input layer. This is often regarded as the hidden layer, and then this is regarded as the output layer. So now what is all this? This is on a very low scale, on a very very, very high level what ChatGPT is. This is on a very, very high level what DALL-E is, or any neural network, or any predictive modeling that is done using deep learning is doing. It is inputted in a certain format. It is passed through something called a hidden layer, and then it's outputted in some way called an output. So now let's look at each of these. So to further hone in on what this format is doing, we can look at a specific example. Let's say this is an image of the number 8. When we humans look at this, our human brains are able to infer that this is an image of a number 8. But computers are not able to. And the computer is not able to just take in an image. It does not know what an image is. It knows what zeros and ones are. So the goal is to convert this into zeros and ones, so the computer is able to understand that, hey, this is an image of the number 8. So how do we do this? So what we can do is we can take the pixel-wise version of this and also convert it to black and white, so that everything other than this middle part, this number 8 part, becomes black, and just in this middle part becomes white. So when we grayscale something, all of these pixel values are going to be closer to 0. Like all the pixel values in general are going to be bounded by 0 and 1. And everything other than this number 8 is going to be very close to 0. And this number 8 will have pixel values that are very close to 1. So what we'll have is essentially 0.3, 0.5, all this made of pixels. So now we have something that is bounded by 0 and 1, and that is represented in terms of numbers. So let's say this image is 28 by 28. So that means how many of these pixel values do we essentially have? So if we do a quick calculation, 28 times 28, that's 784 pixels in total. So now we have 784 numbers. That is what essentially the input layer would be. It would just be a collection of your data represented in numbers. So what we call is or a better terminology would be a vector of information. So it would take your images, your text, whatever, it would convert into a vector of numbers, and that would be your input layer. So right now we have only taken one, but imagine there are 784 more of them just for this one image. So for this one example, let's just take this corner pixel value, which, for example, we can just say A1, which equals to 0.3. Now, this A1 now goes into the hidden layer. So now what is the hidden layer? Hidden layer. The hidden layer consists of a few different parts. So it has something called the weight. It has something called the bias. Something called the linear function. It has something called the activation function. So now what are all these? Essentially, the weight is the importance of something. So if we look at the number 6 and 9, what are the main differences that make 6 different from 9? It is where this little circle thing lasts. And on the 6 it's the bottom, on the 9 it's at the top. So this means that this little pixel value, this little value is what is important. This little position of this value is what is really important to define the number 6 and the number 9. So that is something that is information that is stored in the weight. Now, what is bias? Bias is essentially a way to balance out the weight. So sometimes the weight can be too high, and the bias is a way to bring it down so that there is no favoritism for certain stuff. So essentially, it's just a way to balance something. And this is just a number. So weight is just a number. So let's say we can say this is the number 5, and bias is also just a number. So let's say this is number 10. Now, what is a linear function? Going back to our example, here we only have one of these neurons. So let's just add, here we only have one of these neurons. But imagine we had 784 of these neurons. And all of these neurons, what happens is that in the linear function, so let's just call this L, in the linear function, it takes an A1, so which is one of the inputs, multiplies it by the bias, so multiplies by the weight, and then gets added by the bias. So here we only have one of them. But imagine, so right now here we have 2 of these hidden layers. So this calculation essentially happens twice. So we have A1 to B1 plus A1 1 plus B2 because we have 2 different neurons. But the weights are essentially the same because it's the same input. Once this input changes, the weights are going to change. So we have this, and then we have this. So these two have different biases. So now what is this going to output? This is basically what we call a linear function. This is unbounded. This can have any values, and it is fine for it to be like this because it's in the hidden layer. This number could be 1,000, or this number could be 1. We don't know. And this is when an activation function comes in. When we want to control the output of a neuron, we use something called the activation function. And now the two most common activation function are the softmax and ReLU. We'll come back to something to the softmax, but ReLU is essentially a function that looks something like this, where any value outputted by the linear layer, if it's less than 0, it'll be converted to 0. So it just takes the max of 0 and let's just say L. So it just takes the maximum of whichever of these two values are. So let's say if this value is 10, so we have max of 0 and 10. So which one's higher? 10. So that would mean that this layer right here would output 10. And this, let's say, is a negative value, so this would output 1, 0. So let's just summarize what we have so far. So we have something called A1, which is a neuron, which is associated by some weight. Let's call it weight 1. And then we have another hidden layer, which is essentially another neuron, where we have something called the linear function, where A1 times W1 plus bias 1. All of this as an input. So let me just move this over. So we have all of this as an input to some activation function. So A1 times W1 plus B1. And now we have essentially the same thing, but with a different bias because it's a different neuron and we want to basically balance it out. So now that we have this, these are essentially the two neurons that we just saw earlier. It is all just basically a sequential process of mathematical equations. And now since here there is no, so essentially there's multiple layers, but in this case we only have 2 layers, which is okay. But now let's look at what happens in the final layer. So we have this. So remember this we said was 10, and this we said was 0, based on our activation function, which was we used something called ReLU. Now let's go back to what softmax is. So essentially we have the number 8. What other numbers could this be? This could have been a 0. This could have been a 1. This could have been a 2. This could be any numbers from 0 to, let's say, 0 to 9, because 10, 11 is just a combination of any of these numbers. So it could be either 0 or any number from 0 to 9. So what is a so now what we can do is assign a probability to each of those classes. So let's say this is this output has a probability of 0.9. Let's say this right here represents the number 7. And how do we know that this is the number 7? Well, if the output of these two neurons shows that its probability is 0.9, then it will indeed be 0.7. But if this is, let's say, less than 0.9 and let's say 0.1, then we cannot essentially say this is 0.7. Ideally, the way this would essentially work is that we would have like 9 output layers where all these would go out, and all of these would have some sort of probability values, and based on how we organize this network, we will see whichever one has the highest probability value. That is the value we're going to go with. But for simplicity's sake, we'll just assume that there's only one output right here, and the output of any neural network usually is a probability value. And so we just saw that our initial value is 10 or 0. That is not our probability, because probabilities can only be between 0 and 1. So how do we do this? So now we go back to our initial function, our previously mentioned function called the softmax function. The goal of softmax is essentially to take this value, so that would happen right here. It would take this value and it would just squeeze it to be either 0 or 1 or anything in between. So basically give it a probability. So it's 0.7 or 0.3, whatever. So that, in a way, is what the mathematics of the neural network is. You could start off with input layers, you pass that on to a hidden layer, where in the hidden layer we have things such as the weight, bias, linear function, and activation function, all of which acts together to create an output, and that keeps getting passed on all the way up to the last layer, where all these values are basically squeezed into something that can be represented as a probability using the softmax function, and that is outputted and then interpreted by the user as they seem fit. I guess we can dive into backpropagation gradient descent in a different video. Thank you.